Okay, welcome everyone to HO Colloquium. Today, our speaker is Kai Young from University of Hawaii. Kai did his PhD from Nanjing University, China School of Astronomy and Space Science in 2018. Sorry, sorry. And Kai did his first postdoc from University of Sydney, Sydney Institute for Astronomy during 2019 to 2022. And since 2022 to present, he is a postdoc at Institute for Astronomy in University of Hawaii. Today, Kai will be presenting spectropolarimetric inversion in 4 dimensions with deep learning, a physics-informed machine learning method for 3D solar photosphere reconstruction. To Kai.
Okay. Well, thank you for the invitation. So to give this presentations on some of our progress in the Spin 4D project. And today I will simply talk about some progress in the physically informed machine learning techniques to reconstruct the three-dimensional photosphere reconstructions, photospheres. And here, as you mentioned, that here is an Intel team members here. And then let's go. And the outlines here, I will talk about the goal of the Spin 4D project first, and then we will move to the methods, the technically. And here, the goal of the Spin 4D project. And since with the regular operation of the Daniel K. Noyes Solar Telescope, and it's estimated approximately about in the order of 10 terabyte per data per day. So with such kind of a huge data size, it seems that the traditional one-dimensional inversion with pixel by pixel inversions, it seems a little bit too slow, that we need some new techniques to speed up the inversion. In that way, we can provide in time inversion data methods to produce the decayed data set. And in the traditional inversion, it also means that the inversion mainly provides physical information on the optical depth rather than the height along the site in the space scale. And then we were inspired by the very fast development in the machine learning techniques that you see a lot of very great achievement in both the academia and also in the industry area. So that indicates maybe the deep learning could be a very suitable target for the large volume and high dimensional and nonlinear problems, and it could be parallelized and ultra fast. And such kind of idea was originally demonstrated by the Ascenso Ramos and Diaz Faso in 2019. In their paper, they not only invert the physical parameters in the from the Stokes profile, but also provide their distributions in the geometric height. I mean the Z. Here, could you see my mouse here? And so this provide a very promising result, but currently there are lack of the information about the ambiguity problems, and then our projects are made aim to develop a neural network model for estimating the physical parameters of the solar photosphere, that from the decayed operation and mainly focus on the quasan and the plus regions. And here is a workflow of our Spin 4D project. Usually with the machine learning techniques, we need a large volume of the data set, a paired data set for both the input and the target. Here, and we take the advantage of the relative MHD, the most advanced small scale Dynamo simulations from the Muon. and then we produce the Stokes profile by employ the radiation transfer methods to sensitize it. And combine these two data sets, we train the neural network. And after the training, once if we take a time series Stokes profiles from the decays, and then we can simply through this neural network to predict a time series three-dimensional MHD solar atmosphere. And with those wobbles, we can also derive some second-order properties like the Poynting flux or the helix flux as well. But they are not only one flux in one surface; they are in the 3D, and they contain the time evolving as well. And here, the progress of our project is this: the generation of the training data set in this part is already done, and we have produced 6 small-scale dynamo simulations based on the Rampos 2014 papers. And here I give you the very basic information about the scale of the simulation and the resolution of the simulation and time cadence. And for all of the simulations, we take about 10 million CPU hours, and with the MHD atmosphere, we get about 100 terabyte data volume. And for the Stokes profiles, we mainly focus on the Aaron 1 630 nanometer and 1.5 micron, because these two are mainly focused from the two major lines that focused by the decays instrument and very magnetic sensitive. And we produce the Stokes profile for every 12 minutes and totally generate 20 terabyte data set. And all of the data set I mentioned here can be found for some download linkings in our project webpage here. And then I rephrase this comment, and if since I do not forget the exact word that Matthias used, that just means that if our model mainly focused on the neuron simulations, and it will predict like the neuron solutions, and this is a so-called the out of distribution problems for the machine learning technique, and that's means the neural network will always limited by its training data set. One popular way to solve these problems is to use a large training data set as large as possible to include more parameter space. And this is the most used strategy. And another possible method is that to apply a training data independent approach, such like the physically informed method that we do not need the paired data set. We merely focus on the physics or the law of the physics rather than the data itself, just like the famous physically informed neural networks. And such kind of methods have already proposed in the solar communities, like the nonlinear force-free method by robot ruling in 2019, I guess. Yeah, and then based on these two principles, our project is split into two branches. One is based on the supervised machine learning techniques, and which is ongoing. And our computer scientist is take charge of that and still training and not finished. And for the other one, based on the physically informed and supervised models, and that is used to reconstruct the 3D atmosphere based on the already inverted magnetic fields. This part is done. And I have to mention here that this one can be regarded as some post-processing for the inversion results. So we do not include the inversion here. It's only take the inversion result as an input and produce a final product, a final three-dimensional atmosphere. And let's move to next. Okay, and now let's move to the this technique, the physically informed technique that we mentioned here. And we developed a new code, and I name it as a hierarchical disaggregation decoder. And though we are not only focused on the disaggregation, but also include the geometric heights predictions as well to give a real three-dimensional atmosphere. But this is just a name. And in order to solve these problems and give the three-dimensional atmosphere, we solve two coupled problems, but the immersion is not included. And what's the problems I solved? The first one is one of the most famous problems, the 180-degree ambiguities in the azimuth angles for the inverted magnetic field. So here is an explanation. For the inverted magnetic field along the lump side, it's pretty good. There's no ambiguities. But for the transverse magnetic field, transverse is a perpendicular component to the lump side. It have a two choice of the orientation with 100 degrees. That both of these two orientations give this exactly the same Stokes profile, so that we cannot distinguish them only by the observation from one pixel through the. But the two choices usually will give some very different local radial component, even change the sign of it. So that will be a problem to get a real physical meaningful magnetic field. And the second problem is that the Wilson depression of the optical depth layers. Well, we know that, the optical depth layer is not a perfect flattened surface, and it was moderated by the opacities from the solar atmosphere. And the opacities also be influenced by the temperature, and the temperature was influenced by the magnetic field, because the strong magnetic field will prevent the convections, so that the stronger the magnetic field usually produce a polar temperature that will give a smaller opacity. So in that way, we can look deeper with the colder regions. That's deeper. That means deeper in the strong magnetic field regions. But in the traditional methods, most of those kind of depression was solved with a very smooth solutions. That is due to some numerical issues, the problems of when dealing with such kind of highly spatial, high oscillations in the small scale structures. And both of them, I mentioned that the divergence free equation will play a very important way, like the minimum energy method that's widely used in the solar community, such as a standard pipeline, as the Hinode ISP dataset, and also for the SDO-HMI dataset as well. Well, that was proposed about 30 years ago, and also proposed by the Lipton in 2018 that the divergence-free equation only itself can also solve the problem of these Wilson depressions, but only yet less detailed structure. And so this inspired us that maybe we can solve these two problems altogether, only depends on the divergence-free equation, and reconstruct the three-dimensional magnetic field from the inverted magnetic field on multiple optical layers. And here I gave you a clue about how the divergence equation will help on these two problems. And here I give you a small single cell of the qubit, like in regular qubit like structures, composed with 8 nodes. As here, we have 8 nodes. For each node, we have 2 choice of the azimuth angle for each transverse component. So in this way, we have about 2 to the 8 possible choice of the final orientation for the azimuth angle. Well, in order to build up a 3-dimensional projection for this cell, we need to assign the flow number to be the geometric height of each node, so that we have to assign 8 different float numbers, and only in this way, with the correct magnetic field and the relative positions of them together, we can calculate the net magnetic flux across all of the 6 surfaces of this single cell. And this is what the divergence-free condition help. The divergence-free condition says that the net flux should be 0. And this is how the divergence-free condition add the constraint on the final choice of the orientation of the magnetic field and the geometric height of each pixels. And then this is the case I show here is just an example for one cell. That means 2 pixels in the X and 2 pixels in Y and 2 pixels along the long side. Well, in the real typical observations, usually we will have about 1,000 times 1,000 in X, Y in the field view. And if from typical meaningful inversions, like from the third or the third, we usually have some around 10 to 30 meaningful mesh points in the log 10 in the optical depth. So in that way, we will have a final about 10 to the 7 possible solutions for the azimuth angles. But that is a crazy high numbers. And apart from the azimuth angle orientations, we also have to assign the floating numbers for the geometric height for all of those pixels. This illustrates how the complexity we made. But here, the complexity I mentioned here is only when we consider each node separately. But actually, we will have some correlations information between the nearby pixels. But if we want to take those correlations from the nearby pixels as explicit informations to reconstruct, to solve these 2 problems, it would be very difficult. It would be very difficult in my mind. So we just want to try. Maybe we can take advantage of the deep learning neural network technique to ask the neural network take care of the correlation from the nearby pixels and give us a solution about how to choose the orientation of the magnetic field and how to assign a number for the relative positions for each pixel. This is the original idea and why the divergence-free equation could help to solve these 2 problems for a final 3-dimensional magnetic field. And then, before I go to the detail of the techniques, I have to clarify the coordinate system in case it will make some confusing. And the X, Y I mean here in the observation is in the image plane rather than a local tangential plane. And the Z component is along the long side, and the transverse refer to the component in the XY plane, and the vertical refer to the left side. And then here, as I mentioned, what we have from the information, from the immersion is an inverted ambiguous magnetic field along multiple optical depths. And as here, we organize the inverted magnetic field with a guessed guess the geometric heights with a uniform thickness that we take from the Muron simulation is average. But actually, this is only a very initial initial guidance to tell the neural network, but it does not provide a very high constraint. And indeed, when I personally try for my techniques, is the exact numbers here does not make too much difference. And then the data site, the input data site, data site are organized in the X, Y, and optical depth spanned in the 3 dimension. And then we use 2 unite models to do the data translation from the ambiguous magnetic field to the final physical meaningful magnetic field, and from the intelligent site to give predictions of geometric heights. But they are the united structures to do this translation. And for those who may not know what unite is you can just regard it as a black box that some neural network can do the image or 3-dimensional data cube translation from one to another data site, but without changing the structure of that, but without changing the dimension of that. And this is a very advanced and very widely used architectures based on the convolutional neural network, and we choose to use the 3-dimensional version of that. When we feed our data site into the neural network, we separated them into 2 neural networks. One mainly produce the magnetic field, and the other make predictions on the geometric height, and they are coupled together to give the prediction and the training. Once we have the predictions, we calculate a custom loss functions mainly based on divergence-free equations from these predictions, and based on the custom loss functions, we use the backward propagation technique to calculate the gradient with respect to the hyperparameters, and with the loop iterations to minimize the custom loss functions. And then with the predictions, once if the divergence-free equation minimize sufficiently, we take the input and the predictions out to another step for some post-processing. And before I introduce the post-processing, let me just explain how we construct the custom loss function. That is the key point in our method. For example, here with the predicted magnetic field and the geometric height, we can have a look at about one cell, and the one cell for each single cell, it looks like this. And the divergence-free equation is not measured by the finite difference method, but we make a metric of the integral form. That means the total flux across each surface, and we use a linear interpolation with the values inside the surface. So that means we require the cell could be as small as possible. And then we, with the calculated flux, we try to minimize the flux of the total flux. The loss of the divergence indicates it's a metric of the total net flux, absolute value of the flux, but also it with help with some other regularization to make sure that our predictions is consistent with the inversion with the input. And also some smooth filters is added as well, and we make a vast test to determine the weighting values for each loss term. But I have to be honest that we do not make a fully explore in the space parameters to determine the weighting values, but we only but we still get some optimal solutions for the weighting values here. Then let's go back to the post-processing. Once we take the predictions from the neural network, we can compare the orientations with the orientation of the transverse magnetic field between the prediction and input. We take the difference of the azimuth angle here, and we cite a criteria. Oh, excuse me. Oh, okay. Okay. We take the absolute value of the angle difference. Once if this angle difference is the absolute value is greater than 90 degrees, we just rotate 180 degrees to the input transverse magnetic field. If the condition, if the angle is smaller than 90 degree, okay, just keep it as it is, just keep the input data. And in this way, we get disambiguated magnetic field in the final 3 dimension. But remember, here is this dimension is in the optical depth, not the geometric height. And then since we have a specific unit to predict the geometric height, so equipped with this geometric height, we can translate the optical depth to the geometric height and give finally a 3-dimensional corrugated lower atmosphere with a disambiguated magnetic field. Okay. That is the all of the above is the entire process of how the numerical works, and the test just to try to demonstrate our model can indeed work. And here to test the new technique, we use one of the neuron simulations in our spin-folded data set, on which we modified a small-scale dynamo simulation with an additional with additional 200 gauss in the vertical component, and which mimic the plot regions. And we interpolate the vector magnetic field from the volume from the simulation volume onto 32 optical depth layers that the optical depth range from 0 to -3.1 with a sampling of about 0.1. Yeah. And to mimic the inversion, we modulate the transverse magnetic field to from 0 to pi and -12 pi to half pi. In this way, we just remove the memory about the correct orientations, since all of the azimuth angle are modulated to about 1 pi. And I have to mention that here I made a test with the neuron simulation, but it does not mean our technique is only limited to neuron simulations, since it's a unsupervised technique. And the neuron simulations here is only used to demonstrate we can give a good result. And that means if you give me some data set that looks like this, and how good I can give you a solution back. And then remember, the key point in our method is to minimize the divergence, I mean the total flux of each cell. So here I just present how good it is, and I make a comparison with the normalized reshadow magnetic flux with the average absolute magnetic field strength inside one cell. And in the top panel, I gave these comparisons for our solutions, and the bottom I gave a comparisons from neuron simulation. Well, the neuron simulations, when calculated this metric, we use the exactly correct vector magnetic field and the correct relative projections of each optical layers. Sorry. And it seems that the distributions here looks very, very similar to each other. And if we check the median values of the shadow flux here, it's only about 0.25 gauss, and slightly higher than the data from the ground truth, but I think it's already good enough and almost satisfied. And then let's check about the performance of the disambiguity. That, as I mentioned, I just make a comparison between the predicted azimuth angle and the true azimuth angles here, and we show them versus with the angles and the magnitude of the magnetic field strength, the transverse magnetic field strength here. That is in the log scale in the radar component, and the colors here is in the log scale for the pixel numbers. So that it shows very clear that most of the pixels is clustered close to the angle difference is 0. So that indicates the orientation choose is in this region is correct, and the orientation choose in this region is wrong. And most of the pixels are clustered in this region. That means most of the choice of the orientation in our post-processing could be correct. And then a more statistic comparisons for the to check the capability of the disambiguity is here. With the metric as shown here is a recovery rate that defined with the correct pixels, how much of the correct pixels within the bins can be recovered, and divided by the total pixel bins in these regions, and the bins is divided by the divided in the transverse magnetic field components here. So you see that most of the regions give with a stronger transverse magnetic field give a very good recovery rate, and the blue lines here indicate our solutions, and the orange lines give the solutions from the minimum energy method that I have mentioned that was originally proposed about 30 years ago. And the gray areas here I just present here, but actually it's utilized because the 10 gauss is about the approximate level of the uncertainty from the decay inversion of the transverse magnetic field. But I just kept it as here because I want to show you where our method is completely fail. It fails about around the several below the 1 gauss, and in about 1 gauss, the minimum energy almost goes to only 50% to recover. That means random solutions, but we still keep a solution around 80% here. But in the strong field regions, we almost give a very good solutions all the time. And then, apart from the statistic comparison, let's look at about how the final magnetic field looks like in specific layers. We choose one optical layers as an example to show the magnetic field distributions from the from our method, and and also compare that from the minimum energy method as well. Here in the top one, I gave the ground truth. In the middle one, I gave our solution, and the bottom, I gave the minimum energy solutions. Well, I have to say, in most of the regions with strong magnetic fields, the orientations looks correct in both our solution and the minimum energy solutions. Well, but in some weak field regions, our solution fell, but the minimum energy just survival. And one thing to notify is that from our solutions, the azimuth angle always looks smooth, and even if it fell, no matter if it fell or not. But for the minimum energy, it looks like here we gave a though it's correct here, but it's rather smooth. But the minimum energy will give some zigzag patterns over there that strongly indicate the solution here is not correct. Do not trust them. So that in the usually the minimum energy methods will provide a confidence mask associated with the predictions as well. So that I mean the here is only a comparison, but does not mean we completely win this game. And then we make a quantitative measure of our disability problems, and we actually, apart from the types we have mentioned above, we also may introduce some noisy data set as well to make a test. And here the metric is the total recover rate, about how many pixels we can recover for the entire data volume. It seems here that without the noisy, we can reach about 95% pixel be recovered. With the noisy case, 84%, and give a relative better solutions than the minimum energy solution. And if we go to another metric to compare the recovered Z component of the electric current, with this value B0 is bad and B1 is good. It also indicates we have a relatively better solutions compared with and without noise case. And for another is that because we have recovered the physical meaningful vector magnetic field, so that we can check the difference of the magnetic field strength, and the zero definitely is perfect. And but for others, it can if it's wrong, it can go to infinite. And here, for our solution with and without noises, we goes a rather smaller value, also produce a smaller value than the minimum energy solutions. And then let's move to the geometric height predictions here. I just take one layers from the one optical layers from the ground truth and the predictions here to give a view about how our prediction looks like. It seems that it's very obvious that we are not limited with the only large scale structure, but we can also make predictions in the small scale structures that give a very detailed structure over there. And that is emphasized with these blue circles here. And then if we take a vertical slice here to show the vertical distribution of that, it's likely that we could get a better solutions in the lower atmosphere with a stronger magnetic field, and by a worse solution in the top layers and a relatively weak magnetic field. And then we gave scattered comparison between the predicted geometric height and the ground truth geometric heights, and they are done through the entire computational domain. They give a very high Pearson correlation coefficient, about 0.93. It's very high once if you compare a geometric height and also very high compared to other version depression solvers here. And the right line indicates the identities, and the blue one give you linear fitting results here. The fitting parameters is present here. And they indicate that the colors here is shown in the log scale. So it's very obvious that in this region, it's almost many pixels are in the close to the identical logs. And then equipped with this three-dimensional with the predictions of the geometric height and the disambiguated vector magnetic field, we can reproduce the entire three-dimensional structures of the lower photosphere. Here, I just gave you the movie about, and the top one is the truth, and the bottom one is from our solutions. And from the three-dimensional from the three-dimensional atmosphere, then we can derive the second order, derive some other associated wobbles with the which need to be calculated for the derivatives like divergence and electric current. And here I showed one example of the electric current isosurface distributions. It looks pretty good for me. And then for direct comparison about the electric currents here, is like it seems like there are a lot of strong transverse components can be recovered here. And also the most of the strong electric currents occur in the edge region of the strong magnetic field. And also, we found some sheet-like structure regions here that remember, like in most of the cases, the current sheet. Once if we heard some guy say current sheet, yeah, our mind always go to relate it with some heating event or possible reconnection or somewhere else. And this indicates that if there is some electric current sheet over there, our technique can recover it. And here give a comparison with the statistical comparison about the three components or the vector electric current. It shows they all give very good coefficients and also very good coefficient in the magnitude of the electric current as well. And then with the electric current and the magnetic field, both are disambiguated, we can calculate the Lorentz force in the vector Lorentz force in the three-dimensional atmosphere. So, and we also found that a strong force happened in the edge of the magnetic field, and also this could serve as a direct metric of the non-phosphorinase, other than those present in previously that merely depends on the Maxwell stress integrations because we are lack of the full vector Lorentz force computations. And then statistical comparisons show the absolute magnitude for each component, and the magnitude of Lorentz force also give a very good comparison correlation rate. For the magnitude is even go to the 0.99, it's pretty high. And here I give a summary about the Pearson coefficient for each 3D wobbles from the pure idealized data and with noisy data as well. Both of them give a very high coefficient here. And then we move to the summary of this technique. It seems that we use the 3D unit and combine it with the divergence-free equation, and they can solve the problems, very complicated problems of reconstructing the three-dimensional photosphere based on the inverted magnetic field. It solved the two problems with very high complexities in the degree of freedom. And also, this technique is a simulation-free, simulation independent. But to be honest, because it is unsupervised methods and physically informed methods, so it will take a little bit longer than the typical unit work. And then it enable the derivations of the 3D vector electric current calculation and the Lorentz force, which was rarely reported in the previous research. And also it can recover the very small structures, and also, I think it's rarely reported in the previous observations. And I think most of you are interested into the results, to the science results for the application onto the decades. But I will not present that, but I have to say it will come soon. Yeah, and that's all. Thanks.
Thank you. So people can ask questions. And from online, please unmute and ask your question. Actually, I have a question. So when you use model output, I assume that you add those you add error because those are pure data, and you add error to make it real data. So
Yeah.
what is I mean noise? You call it noise. So what is the scheme for adding noise?
Oh, the
Like,
screen. You mean
like
how I dealt with the noisy data?
yeah, I know how you create noisy data from pure simulation data. For example, I'm asking this because in data simulation for Kalman creating Kalman filter, people generally use Gaussian type noise in the real data in the model data to make it synthetic data. So, what is your scheme?
Oh, in my strategy, in my choice for the noisy data, see, I just use a random Gaussian noise with a
Okay.
typical scale. I think it's about around 10 Gauss,
Okay.
and then. But we remember that we usually make some cleaner noisy filters in our realistic or in our realistic observations. So in that way, after I added the random noise into the data, and then I apply a medium filter as well to remove the paper-like noise over there, and then import those data to the neural network to check the capability of it. Just try to mimic the real data processings.
Right. Thank you. Other questions? And from on, oh, Michael.
Yeah.
Please wait. Michael is asking a question.
So you took model output and you admit, and we all know that the physics description of the scenario on the sun is imperfect because certain things we have not under control yet. Is it feasible that by teaching your analysis with quote unquote imperfect models, that we get output that always looks reasonable, but we are missing something decisive? Or in other words, is there any way of checking with real observations if you assume, if you apply this method a discrepancy between the reality on the sun and your vast array of models that are sort of the library of solutions?
Oh, do you mean that? Let me just repeat the question, see if in case I'm wrong. And do you mean that whether I can check whether the through our methods, whether the simulations predictions from that is consistent with the physics really happened on the sun, because the simulations have contains a lot of additional assumptions that may not that kind of realistic. Am I right in that way?
I haven't understood the question.
You were just rephrasing your question to make sure he understood it correctly, Michael.
Yeah, I didn't understand.
Okay.
Can you reformulate it?
Do you mean that you want me to whether I can check what real happened on the sun compared to the neurons the simulations like neurons through our methods to check the discrepancy between those?
I'm gonna try to formulate it very simply. Will we ever find out whether something is wrong with our picture? With this method?
Well, I didn't get that deeper to think about what is wrong or not. But we just try to maybe to take the effort to try to how that could be done. But the false or true for some specific instructions, I'm not exactly sure. Maybe, I mean, if maybe we can, since our method is applied to the magnetic field rather than the immersion itself, that we can take a series of different methods to do the immersion that provide independent immersion at the same time and apply the technique to all of them and check the discrepancy. And if there's something common, that maybe we can say this we will have some high confidence on this specific things. And if our many different immersion provide results share the give a diverse result, then we can see a less confidence on those.
Yeah, I'm not sure I share your confidence, but I think if this is applied many cases, we know more. Thank you.
Okay,
thank you for your comments.
Phil.
Phil?
Yeah, thank you. Hi, that was a very nice talk. I think you're doing something very important, and I think I understood Michael's question in the end. So, but I won't talk about that. I have a couple of points. One is this would require measurements of spectral lines at multiple heights of IQ, U, and V over an area of magnetic field because you're using spatial information. So does DKIST have an instrument that could do this at this stage?
Well, yes. The currently we have applied the technique to WISP, the visible infrared spectropolarimetric polarimetry, and another the Ionosphere can do it as well, and also the I think the upcoming VTF can do it as well.
Yeah, it seems as if you may not have enough time to do all that. Certainly not with a slit spectrometer. You're going to need an imaging spectrometer. On the other hand, then you've got to scan in wavelength, and the solar environment is going to change on those time scales.
Yeah.
So
Yeah.
that I'm just wondering I'm just pointing that out because in the future, this might influence the choice of instruments. Another point is that I've argued many years ago that we need to get a very good longitudinal polarimeter in an angle different from the Earth's sun line, so you can really check your azimuthal things. And I've argued for a mission to do that, but it's too expensive, and I think people have made a career out of trying to figure out how to remove the ambiguity. But I think the only way to do it really is to measure it, and that would answer some of Michael's questions. And then my final point is very simple. I appreciate you get the Lorentz force out of your analysis, and I think I understand how you do it. I would like to get the pointing vector out of that, but I think you need the three components of velocity,
Exactly.
which would again argue for an instrument away from the Earth sun line, at least one. But I'm wondering if there's a way to, for instance, you might set div V equals 0, as well as div B equals 0, and then see. I'm just wondering if you thought about trying to get this V cross B cross B out of a data like this.
Well, actually, so for the velocity considerations, I actually current which we do not touch, and with the time we need some kind of time series and some assumptions for the equations, and that way. But that will be our next step, and to take a detailed consideration about that.
Okay, great.
And also I think yes, and our current manuscript will also notice that your paper several years ago to talk about multi-angle. Yes, definitely that will be that will be the real solid solutions to solve this ambiguity problem. And I think the solar orbiter, some experiment produced by the solar orbiter have realized that, but that the resolution of that is not that kind of high, and it's barely compared with the joint observations with HMI and Phi on board the solar orbiters, but very few cases.
Yeah, so earlier, just one final point. I published a paper on the multi-directional spacecraft needs the stereoscopic view of the longitudinal field. And in that one, I pointed out that you should do it in the ultraviolet with a small telescope, because then that will be first order in the Zeeman effect. So you don't even attempt to measure the tangent, the transverse components, but also you gain in angular resolution. So you get something that might well be able to do that. And the obvious spectrum to use for that is iron 1. So you can observe iron 1 in the infrared with DKIST, and you could observe iron 1 in the ultraviolet from space, and that combination would resolve many of the ambiguities and reveal the strength or weaknesses of various methods. So at that, I'll be quiet and thank you again.
Oh, thank you.
Any other question?
Yeah, how big a telescope would you need in space to gather enough photons?
40 centimeter, because you're just measuring Stokes V, not Q and U. That's plenty big enough. We actually discussed this as part of the efforts towards building what ultimately became a CMEX proposal. Which we will find out sometime this month, I guess, if there's a NASA still.
I have another question. When this method that you described in your presentation would be applied regularly on observations, what would the processing effort look like?
And which kind of post processing do you refer to? You mean the post processing I introduced in the step 2 in our method, or some processing say, for the inverted magnetic field before we feed the data into the neural network?
Do you mean how much computational resources are required to do it?
How long would it
Yeah.
take, given
Oh,
the
okay.
computational?
Well, to be honest, the current models I applied to the test case, the test case is spanned with 256 pixels times 256 pixels times to 32 layers. And I make it work on 2 V100 GPU chips, and it runs for around 10 hours. Yeah.
And I mean, in a true application, one would would like to look at a much larger number.
And to the realistic observations, and I think the time could be compatible or even longer. And also that depends on how many computational resource the GPU chips we can access. Currently, I only make it work on the 2 V100 GPU chips. And if we have more advanced GPU chips with about like 10 chips or 5 or 8 chips, it could be time could be highly reduced.
Related to this, Kai, did you test when you have a time series and you kind of, for the next time step, you use the reconstructed heights from the previous time step as initial state, whether that speeds up the problem significantly?
I guess it should, but I didn't make a test in that way. And we check the generality in the other way to apply it to the untrained data set, as I mentioned. Maybe you didn't have a look at about our appendix in the manuscript, but here, sorry, I didn't show this one, but this is just to show the generalizations on the IC data. See here, so if we only train the neural networks with the inside data in this box, and to apply the neural network to the entire volume, it seems even in the margin, the margin regions that are without training, it can give a relatively pretty good solution as well. So as you mentioned, that if I apply to the second time, I guess if the magnetic field structures, I mean, the information does not change too much, I guess it should give a pretty good solution as well, and give a faster convergence as well.
Is it feasible that ultimately this could be a user tool that could be applied as sort of a general step in the data analysis by anybody?
Well, I think currently I have hosted this code in the GitHub, so everyone can download it. But whether any user can use it, it depends on whether you can have access to GPU chips. And since it's not a usual GPU heavily cost, so I think even limited GPU access could be used. So I guess, yeah, it could be.
Thank you.
Thank you.
Anyone else? Any question? And from online? Okay. If not, let's thank our speaker again.
Thank you.
Okay.